Hi student, good evening. So today we are going to see what? Today we are going to see the condition for Boltzmann approximation. Yes, condition for Boltzmann approximation. When we are allowed to take this Boltzmann approximation, is there any condition or we are blindly taking it as in the calculation in order to calculate the concentration of charge carrier? Okay, so we will see what condition for Boltzmann approximation. Today's topic is what? Topic is condition for Boltzmann approximation. Okay, the condition today's condition for Boltzmann approximation. Okay, Boltzmann approximation. Condition for Boltzmann approximation. Okay, the condition for Boltzmann approximation. This is our topic today. Now, we want to see that this Boltzmann approximation f of e is equal to what? E to the power minus ef by kt. This is our Boltzmann approximation. Yes, this is our Boltzmann approximation when it is valid. Is it always that we can take it in the account for the calculation of charge carrier concentration as electrons and hole? And is there any condition? Yes, there is a condition when we have to take this Boltzmann approximation. Okay, otherwise we have to take only Fermi direct distribution function in order to calculate the concentration of charge carrier. Okay, so it is very important to know about this when we have to take this Boltzmann approximation into the account in order to calculate the charge carrier concentration. Let us see the Fermi direct distribution function. First of all, you should know the Fermi direct distribution function and Boltzmann approximation. Fermi direct distribution function and Boltzmann approximation are related to. Okay, these are within 5% to each other. 5% to each other. Okay, 5% to each other. Okay, so this is the condition. What is the condition? Condition is that when the Fermi direct distribution function and Boltzmann approximation are within 5% to each other, then in that case we are allowed to take Boltzmann. We are allowed to take Boltzmann approximation. Okay, we are allowed to take Boltzmann approximation into account in order to calculate carrier concentration. Okay, so these are the condition. What is condition? Condition is the Fermi direct distribution function and Boltzmann approximation. They should be 5% to each other, then in that case we are allowed to take the Boltzmann approximation into account in order to calculate the carrier concentration. that may be electron and hole concentration, right? Electron concentration. N is equal to what? N is equal to NC NC into e to the power EC minus EF by KT. Okay. Or whole P is equal to NV is equal to e to the power minus e to the power minus EF minus EV. Yes, EF minus EV by KT. Yes. So these are the conditions. EF minus EV by KT. Okay. So what are the conditions? Condition is that Fermi direct distribution function and Boltzmann approximation, they should both be within 5% to each other. Okay, 5% to each other. Only in that case we are allowed to take the Boltzmann approximation into the account. Okay, into the account. Now see what extent we should increase. We should increase the energy state okay, above the Fermi energy level, so that we are able to take this Fermi direct distribution function. I mean that, see here, this is what my Fermi energy level. Okay, I mean to say that what, how much above I have to take, how much above I have to shift the energy state by an amount of KT. Okay, by an amount of KT. That is what E minus EF by KT. That is what E. Okay, so if you see here, E is equal to what? KT. Yes, KT. So this is nothing but E minus EF greater than KT. Yes, this means what? E greater than EF plus KT. So this means what? This is what? Greater than KT. This means what? How much above? EF plus KT. Means how much above I have to shift this energy level. This energy level. Okay, this energy level. How much above I have to shift this energy level? This energy level, so that I am able to take the approximation of both. I am able to take the Boltzmann approximation into account. Okay, by an amount of KT. How much above? By an amount of KT, I should shift above this Fermi energy level. Okay, Fermi energy level. Okay, what I means how much above I should shift this available energy state above EF by an amount of KT. KT, so that I am able to take the Boltzmann approximation into account in order to calculate the carrier concentration. Okay, in order to calculate the carrier concentration, means how much above we have to shift. Okay, but this is confirmed. Okay, concept within mind. Okay, so we are going to derive the expression based on this. Okay, so now see what are the conditions. So that is very important, because otherwise we get habituated to take always this expression. Might be it is valid or it is not valid. Okay, so we should check first. Now see here, what is the condition? Condition is that Fermi direct. Condition is that Boltzmann approximation and Fermi direct distribution function difference that should be within what? Within 5%. Yes, within 5%. That should be within 5%. Yes, both should be in 5%. Now see, what is it? What is this? Put the value of this e to the power minus e minus f by kt minus f of e is nothing but 1 by 1 plus e to the power e minus ef by kt. Yes, by kt is what? Less than equal to 5%. Yes, now solve this. When you solve this, what we will get here? E to the power minus e minus ef by kt, okay, by kt, just multiply this will get cancelled, plus 1, okay, plus 1 minus 1, yes, minus 1 divided by 1 plus e to the power e minus ef by kt is equal to what? Is less than equal to what? 5%. Okay, now see, 1 will get cancelled. Yes, now e to the power minus now see, this is okay. So now e to the power minus e minus ef by kt is equal to 5% of, is equal to 1 plus e to the power e minus ef by kt into 5%. Okay, this is less than equal to. Okay, so now, sorry, this is what? This difference is what? This difference is actually within 5%. Within 5% of what? Within 5% of this. Within 5% of this. This difference is within 5% of. Okay, so this difference should be, okay, this difference is nothing but within the 5% of what? 5% of Fermi-Dirac distribution function. Okay, this difference is less than equal to 5% of this Fermi-Dirac distribution function. Okay, Fermi-Dirac distribution function. So now see here, this is my Fermi-Dirac distribution function. So which is nothing but, we should write here a Fermi-Dirac distribution function f of e. Okay, so now just write here this value. This is what? 1 by 1 plus e to the power e minus ef by kt, okay, by kt into 5%, okay. Now this is what? 5% of what? Okay, so this is 5% of f of e. Remember, this is f of e, 5% of f of e. Okay, so now let us remove this here. We have got this, okay, 5% of this. Now up to this is okay. So 5% of f of e. Okay, we should take this. This is nothing but e to the power minus e minus ef by kt, then it is plus 1 minus 1, okay, divided by e to the power e minus ef by kt is equal to 5% of f of e. This, okay. So then this implies what? This implies this, okay. So this will get cancelled, okay, cancel, and we are left with what? We are left with e minus ef. We are left with what? We are left with e minus ef by kt. Kt is equal to what? Kt is less than equal to what? Kt is less than equal to 5%. What? 5%. Okay. We are left with this. Okay. E to the power e minus ef by kt is equal to 5%. Okay. 5%. Now see here. Let us take this side. Let us take this side. E to the power E minus EF by kt is equal to 1 by 5%. 1 by 5%, which is nothing but 100 by 5, which is nothing but 20. Okay. So now see here, E minus EF by kt. E minus EF by kt is equal to what? Is equal to ln 20. Yes, ln 20. Now see, E minus EF is equal to kt ln 20. What is this? E minus EF is equal to kt ln 20 is how much? 2.993 kt. Yes. So which is approximately equal to what? Which is approximately equal to 3 kt. 3 kt. Yes. This is what? This is greater than equality sign. Greater than equal to. Greater than equal to. Okay. So this is greater than equal to. This is greater than equal to. Greater than equal to. Okay. So now up to this is okay. So E minus EF is greater than equal to 3 kt. Okay. So this is what? E minus EF is at least what? At least 3 kt. 3 kt. Okay. 3 kt. Now see, 3 kt. So this is what? This is the condition. This is condition. What condition is that? E minus EF. Okay. What is the condition that E minus EF should be at least, E minus EF should be at least 3 kt. At least 3 kt means what? Here I want to make you understand. Here I want to make you understand what exactly mean what. Exactly mean what? See here. Now this. Finally we got what? E minus EF should be what? Should be at least 3 kt. At least 3 kt. Okay. E minus EF should be at least 3 kt. This implies that what? This implies that Fermi direct distribution function. Fermi direct distribution function is approximately equal to Boltzmann approximation, e to the power minus EF by kt. Remember, this is possible only in this condition only. Okay. Note it please. This is possible. This is possible only when we have this condition. We have this condition. Okay. We have this condition, and which implies that carrier concentration N is equal to Nc into e to the power minus Ec minus Ef by kt. Okay. So by kt, or P is equal to Nb e to the power E minus e to the power Ef minus Cv by kt. Okay. So this is what? This is all possible only when this all is possible only when we have E minus Ef by kt. This means what? See here. This is my Fermi energy level. This is my Fermi energy level. Then how much above I have to go? How much above I have to go? I have to jump 3 kt. I have to jump 3 kt above EF. I have to jump 3 kt above EF. Then only I am eligible to take the Boltzmann approximation into the account in order to calculate the carrier concentration. Okay. In order to take the carrier concentration into the account. Okay. In order to calculate the carrier concentration is possible only when this E minus Ef is greater than 3 kt. Okay. E minus Ef is greater than 3 kt. If this condition is not valid, okay, if this condition is not achieved, then we are no longer to take this Boltzmann approximation into account for the consent in order to calculate the carrier concentration. Okay, so this is very important. Now see, at room temperature, for example, at room temperature, okay, for example, at 300 degree Kelvin, at 300 degree Kelvin, how much we have to shift above 300 degree Kelvin? What is this 3 kT? 3 kT means what? 3 kT means what? If you see here 3 into what? 3 into K is Boltzmann approximation, kT. Okay, Boltzmann approximation kT by Q. We will see kT by Q. Okay, in term of electron volt. Okay, in term of electron volt, how much we have to shift in term of electron volt is what? 3 into what? This is kT. K is what? Boltzmann approximation is temperature, which is nothing but what? 300 divided by 11,600. Okay, which is nothing but 3 into what? 0.02586. okay, which is nothing but what? 77. So which is nothing but 0.07758 electron volt, which means 77.58 electron volt. Yes, how much? This is nothing but 77.58 milli electron volt. Okay, milli electron volt at room temperature. At room temperature. So this means what? E minus EF. E minus EF should be this much. This much means what? You should be above what? 70. This is what? 77.58 electron volt. Electron volt. Okay, so this is what? 77.58 electron volt. If you are above the Fermi energy level, then you are what? Then you are eligible to take this Boltzmann approximation into the account in order to calculate the carrier concentration. Okay, otherwise it is not possible to take. It is not. Okay, so otherwise it is not valid. It is not valid. Okay, so remember, this is very important condition you have to take into account. Okay, so this is very important condition. Okay, what is the condition? What is the condition that we are taking this Boltzmann approximation under what condition? Under this condition. What condition? This condition means how much above? How much above you have to shift? You have to shift this energy state above the Fermi energy. Above the Fermi energy. How much above? This much. 3 kT. 3 kT means what? Under room temperature 77.58. 77.58 milli electron volt. What? Milli electron volt. Okay. You have to shift this much. You have to shift this much above, then only you are eligible to take this Boltzmann approximation into account in order to calculate this charge carrier concentration. Okay, if it is not valid, then you have to deal with what? Or you have to deal with Fermi direct distribution function. Okay, so this is only the case for this Fermi energy level. Okay, so how much above you have to shift, okay, in order to take the Boltzmann approximation into account. Yes, is it okay? So just take it, just note down this how much value we should take under room temperature. This is for under room temperature. Okay, so now see, this is all about the condition of Boltzmann approximation. Yes, this is all about the condition about Boltzmann approximation when we have to take this under this Boltzmann approximation into the account in order to calculate the charge carrier concentration. If this condition is not there, okay, if we are not satisfying this condition, then we are no longer to take this Boltzmann approximation. Then we have to go for Fermi direct distribution function in order to calculate the charge carrier concentration. Okay, see this what? If it is not valid, okay, if it is not satisfying, then what? If it is not satisfying, then what? See here, if Boltzmann approximation condition, if Boltzmann approximation condition, if Boltzmann approximation condition is not satisfying, then what? Satisfying is not satisfying, then we have to deal with Fermi direct distribution function. Fermi direct distribution function. We have to deal with Fermi direct distribution function. Okay, we have to deal with Fermi direct distribution function. Okay, so for the calculation of what charge carrier concentration, let us see how to calculate the charge carrier concentration. N is equal to, for generally how to calculate, N is equal to integration EC to what? Infinity. EC to infinity G of E F of E dE. Okay, you have to deal like this. Integration EC to what? Infinity. G of E is what? 4 pi 2mn star to the power 3 by 2 divided by h cube square root of E minus EC. Okay, E minus EC into 1 by 1 plus E to the power E minus EF by KT, E minus EF by KT. Okay, into DE. Okay, you have to deal with this. If it is not possible, you have to deal with this. You cannot neglect this. If E minus EF is less than or equal to, if E minus EF is less than 70, less than 3 kT, let us say 3 kT, less than 3 kT, then you have to take into account this. Okay, you can't neglect this under this condition. What? If E minus EF is less than 3 kT. Okay, we are habituated this because in 99% of the problem we are doing all the problem with Boltzmann approximation only. Okay, if by default, if at all this condition is not valid, then how you can solve? Okay, you can solve by general method. Okay, so for that E minus EF is less than 3 kT, then we have to solve with general method. For general method is this only. Okay, for this only. For what we can get N is equal to what? N is equal to, so this is what N is equal to 2 by root pi. It will come N is equal to 2 by root pi NC into Fermi function half of eta. So this is the way to calculation. Okay, calculation of charge carrier concentration when E minus EF is less than 3 kT. This is when E minus EF. Okay, when E minus EF is less than 3 kT. When E minus EF is less than 3 kT, then you have to deal with this. Okay, this is what Fermi integral. This is nothing but Fermi integral. F half is equal to F half eta. F half eta is nothing but is equal to integration. This is my eta F. Okay, this eta F is nothing but 0 to infinity square root of eta F. Okay, so this we have to deal with this. Okay, where eta is what? Where eta is nothing but E minus EC by KT. Where eta is nothing but E minus EC by KT, and eta F is nothing but E F minus EC by KT. Yes, you have to deal this. Okay, so this is only the way to solve. Okay, so by default, okay, if at all this condition is not valid, if at all this condition is not satisfied, then how to solve? This is general method. Okay, just remember this only. You have to remember this only. What this? You have to remember this only. Then go to this. Okay. In this way, you can calculate 2 by root pi NC f half eta. This is nothing but Fermi direct integral. F eta half f. Okay. So let us I will write this properly. So if Boltzmann approximation is not valid, okay, if Boltzmann approximation is not valid, see here, if Boltzmann approximation is not valid, if E minus EF is less than 3 kT, if E minus EF is less than 3 kT, then what? Then and not. Then what? Concentration of charge carrier N is equal to what? N is equal to integration EC to infinity G of E into f of E dE, f of E dE. Okay, so N is equal to what? N is equal to integration EC. What? EC to infinity. Just put this all value 4 pi to mn star to the power 3 by 2 by h cube into 1 by 1 plus e to the power e minus ef by kt, okay, by kt dE, okay, dE. So you have to solve like this. Okay, so don't, okay, I will give direct expression. You have to put all value there. Okay, you can get. No need to solve this directly. Okay, so just you remember this expression. N is equal to 2 by root pi NC into this Fermi direct integral f half eta f. You remember this. Just okay. So f half eta f is nothing but f half eta f is nothing but equal to integration. What? Integration 0 to infinity square root of eta d eta divided by 1 plus e to the power eta minus eta f. Okay, eta minus eta f. Just you remember this. Where eta is nothing but e minus e c by k t. Okay, and eta f is nothing but eta ef minus ec by k t. Okay, so this only you have to remember this. Okay, this expression only, this much only you have to remember. Okay, so just you know NC, okay, and this is fixed value of NC. Okay, this is Fermi direct integral. Fermi direct integral value is this 0 to infinity square root of eta d eta divided by 1 plus e to the power eta minus eta f. Okay, eta is nothing but e minus ec by kt, eta f is nothing but ef minus ec by kt. Okay, so this is only what? This is only when e minus ef minus what? E minus ef is less than 3 kt. Okay, when you are solving some problem. Okay, right? If at all it is not satisfying, means at room temperature, let us say room temperature is given for you 300 Kelvin. Okay, just you have to put here only 3 kt. How much is this? At room temperature, this is nothing but 77.58 what milli electron volt. Okay, if it is coming greater than or equal to this, then you can take Boltzmann approximation. And if at all it is not satisfying, it is coming less than this, then it is not valid. You have to solve this. You have to solve by this approach. Okay, if it is greater than, you have to solve by this approach. If it is less than, you have to solve by this approach. Okay, so these are the some valid condition. Okay, valid condition for the calculation of charge carrier concentration. Okay, whether at which time, at what time you have to take Boltzmann approximation into account, or at what time you have not to take this Boltzmann approximation into account. Okay, now I think you are understood. Okay, you are understood about this Boltzmann approximation condition, when to take, when not to take, when to take when it is greater than 3 kt. Okay, when not to take when it is less than 3 kt. Okay, that time you have to take this. Okay, you have to solve like this. Nothing is there, nothing difficulty. Okay, I have given you direct expression. Okay, no need to solve this, directly do this. Okay, just put this value, or NC is fixed value, just you can remember that. Okay, so this is expression for this. Okay, so there is not at all any problem now. Okay, any problem now? We have completed everything in this Fermi direct distribution function. Okay, so that's all for today, and thank you very much. Okay, so this is all about Fermi direct distribution function. Okay, and about Boltzmann approximation. We have done everything with this by drawing graph and by drawing mathematical derivation. Okay, we have done everything. Okay, so now we are confirmed about what to take, what not to take, when to take Boltzmann approximation, when not to take the Boltzmann approximation condition. Okay, you have to remember this point. Okay, this point at room temperature how much? 77.58 milli electron volt. If it is coming less than, then if you are solving by this approach, then it is wrong. If you are solving by this approach, then it is right. Okay, so that's all for today. Thank you very much.